start the recording, just for the sake of also putting this up. Then it's going to begin. So to begin with it, hopefully some of you understand C to a decent degree. If you don't, definitely a good way to start would be this resource. Button. This resource here is really, really nice. The reason why is because it's basically just one big source code file, which means that you can run basically everything here. And not only that, it basically tells you everything you need to know about it. And there's some stuff here that's not necessarily that important, but there's some stuff here that's really awesome, such as like how arithmetic works, comparisons, logical operations, bitwise operations, which we're going to be covering later and hopefully covered a bit in cheats and in lectures. But anyway, so this is a very good way to do it. If you really need a recap, you can just kind of go Control Command F, find what you need to find. For example, I don't know, hash defines, I guess. You can see here. Oh, here's all the hash define information. Okay. I don't care about the course outline. I should just close that. So we're going to begin with this C program here. We're going to talk about accessibility. So the first thing that we notice about this program here is that there's three functions. There's some global variables, right? There's A, B, E, and G, followed by some local variables, H, I, and F, and C, D, and then a static local function, a static local variable. Other than that, there's also unsigned integers and normal integers. Hopefully you've covered that in lectures, but if you haven't, I'll probably give a brief explanation of it later. That's not really important for this treat though, right? So for now, you can just think of an unsigned number as being always positive. Static is what we're going to talk about in a second. Static means something different in every single programming language. So it's one of the most annoying keywords. It gets overused way too much. Static, so static means two things in C, which is fun. The first thing about static is it means if you use it for a global variable, it means it can only be used in that file effectively, right? So it's really nice. Well, more importantly, it means it can only be used, it means it can't collide with other. Okay, there's a really complex definition, but yes, effectively, it can only be used in that file. Right? The complex definition is due to something called translation units, which is like when you compile multiple C files concurrently, and all those C files have different translation units, but their variables can collide if they're global. But if they're static, they won't, because static units live within their translation unit. But you don't have to worry about that. Effectively, if it's static here, it means it can only be used in that file. But if it's static here, that's not necessarily true. So a static variable here can only be accessed within this function, right? But it's still global, right? Yeah. So basically, this FF is still a global variable, but can only be accessed within this function, which means if I modify it within this function, it will retain its value between function calls, right? So a classic way I can kind of show what I mean by this is if I have something like this, create a new file, change language mode, see, I create my void function here. And then I also do a inc function, right? And say I make this return a integer actually. I can create like a static integer here, I, and I can say return I++, right? So what this will do is every time I call it, the value will increment. So this first time it's going to be 0 because it's I++, which means it's going to return the original value of I, then increment it. Then it's going to be 1, then it's going to be 2, and it's going to be 3, and so on, right? Because the static variable here is basically the same thing as if I did this. Right? But the difference is that I can't access it inside of here, right? So it's basically just like binding a variable to a function. Now, if you're in other languages, again, it means something very, very different, but in here will be this. Yes, it will still return 1. Reason why is this variable has a lifetime. Inc just stands for increment. It's just a short name. Like incrementing means like +1. So it's just like add 1, basically. Yeah, so here, if this was static, I couldn't go printf I. is hidden. Its main purpose is a few things, and effectively it's to construct, it's typically to construct resources that can't be constructed at compile time, and that still needs some kind of initialization. So for example, I'll just talk through this first, then I'll talk about it. So if we have a struct here, right, and a struct is just like a way to collect multiple objects into a single thing, right? And let's say I create my struct and I call this like game engine, right? This game engine could have a bunch of different properties inside of it, like let's say, for example, a count of entities alive. Now, when we want to create this game engine here, get engine, we may want this engine to always exist, right? And only ever have one engine. And so what we can use is we can use something called like a singleton pattern, which is basically where we create the game engine in like a static variable. Obviously, I'm presuming that this is a single-threaded program. Otherwise, I may want to like use locks and stuff. But anyway, so I can create my singleton here. And then all I can do is I can check if the singleton equals null, which will only ever equal null on the first time this function gets called, right? Because it's going to be initialized null here. And if is, I can initialize it. And I added that in the wrong place, right? And singleton just, I believe, basically just means like one. I don't know what ton means, but its origin probably just means like one of something, right? And so in this case, I can do something like singleton count of entities 5 equals 0. And something, right? Return singleton. So this way, I can have a function that initializes the variable at runtime, because obviously I can't do malloc when this program initializes, but still kind of persist the value throughout. And so there's various other ways we can use static variables, but that's the main reason. Again, not relevant really for this course. I don't really even know why they mention it, but still. What's the difference between this and using pointers? Pointers are very different. So this doesn't really have, oh, that's just convention. That's just convention. This could just be called singleton. I just use all my static functions, like an underscore, just to indicate to me when I'm reading the code, even if it's like really, really far down, that it's a static variable. A pointer and this is very different, right? So this is basically just as if I declared up here and I'm just using it inside of here, right? There's really no difference between these two. And it's just by controlling lifetime. No worries, I'll talk about malloc in a second. Whereas using a pointer is effectively just taking the address of an object, right? So the whole idea of computers and specifically relating to objects is we care about two things of an object. And the first thing we care about is its location in memory. And the second thing that we care about is its value, right? Ray's had a question before. If you still got a question, keep your hand up and I'll come to it. And so the first thing that we care about is, as I said, the value, right? And so, for example, the value of this is null, right? This is the value of it. Even though it's a pointer, right? The pointer object still has to be stored somewhere. This is what confuses people. And so if I create an int here, and this is 0, right? The value of this int is 0, but it also holds an address. And so the address of this int could be 1,000. And so what this means is that if we have memory, and memory can kind of at this point be thought as one big array, we'll later on find that interpretation is wrong, but right now it can. So we have one big array and an address 1,000, we have the value of int, right? But int, if you know a little bit about integers, is integers are 4 bytes, right? And so what that means is that like they're 32 bits, or that they can store a number that's pretty large, right? And so for the first address, this will be X, but so will the second address and the third address and the fourth address, right? And so if we look at this as our memory, this is going to be address 1000, right? And so when we take a pointer to a variable, we're basically just creating an object, right, that has this as its value, right? The pointer itself will also have an address because the pointer itself will also have to be located somewhere. So for example, this singleton will most likely be located right after the X. So it would be somewhere here. And this would be, well, this is going to be 1,000. This would be 1,004, right? No. Right? So the answer is, even though everything is 8 bits, right, we still address it in terms of bytes. So this would be 1,000, 1,001, 1,002, 1,004, 1,003, and this would start off at 1,004, right? Because 1, 2, 3, 4. And so our next object here would be our singleton, right? Which would consist of 8 bytes. You don't really have to care about why, it's just pointers 8 bytes are going to be on my system and most likely your system, right? And the main reason why is because we're using 64-bit computers, right? So what that means is that the bus width is 64 bits, which means that we can send 64 bits of information anywhere. That doesn't necessarily mean the pointers have to be 64-bit, but typically indicates that. There's a few systems where that is not true, but no modern systems. And so in this case, my singleton is going to be 8 bytes long, right? But it's also going to have an address, even if that address is 1,004 and its value is yet say pointing at x. So for example, if we change this to an integer pointer, right? This value here is going to be 1,000, right? So it's going to point back to x, but it also exists as an object, right? And so this is the thing that's really important with C, and it's kind of hard to get, and it will probably take you a while. But the base idea of C is that you kind of probably learned this concept of pass by reference and pass by value. So the idea of a pass by reference and pass by value is that pass by reference is, for example, like scanf, right? So I'm scanning in an integer here, and I'm passing x by reference. Right? And pass by value would be something like printf, right? Where you're passing the value of the object, right? So the value of x rather than its location. Now, in reality, these are both the exact same thing. In C, there's only pass by value, right? Which is why when you go like struct, or for example, game engine here, if I create a struct game engine A and I go the same thing for B, it's just going to copy this struct. Like everything in C is copied, right? The only difference here is I'm creating a pointer, then passing that pointer by value, right? Just like what I set up here, right? I'm creating a pointer to X, which I can call whatever, like at X, right? I'm putting it somewhere on my location memory, right? Maybe placed somewhere in my memory. Maybe this is a register. Maybe it's main memory. Like this is main memory. It's probably not going to be placed on main memory, but it's simple to think of it that way. And then I'm just passing the value of that pointer, which is 1,000, right? Because that's what I said where X lives, right? I'm passing that by value into scanf, right? And so basically everything when it comes down to it is integers. In programming and C and computers, almost everything is an integer. Even floats are effectively just an integer that we're interpreting in a different way than we normally do, right? Like, do you know movies where everything's like zeros and ones and that's like programming, right? Effectively, that's true, right? Everything is a 0 and 1, right? It's just sometimes easier to think of them as integers rather than as just raw binary. And so that's a bit of a deviation, but effectively here from that, we can acknowledge that the variables accessible within main are obviously going to be its local variables. It's obviously going to be G and E and A and B, right? Because they're globals. But the only ones it can't access are things inside function 1 because it can't see these. Like these are hidden by this function here. I'll talk about malloc in a few seconds. And it can't see anything inside function 2. So as I said, it won't be able to see the static variable, right? Because static means that it's bound to that function. So its lifetime exists, even though its lifetime exists independently to that function, it's still bound to it. Oh, wait, yeah, that's a question.
Yeah, I was just static variables, we can make them in structs or whatever functions we want. But if we can't print them in the main function, then I'm just wondering, can we pass their value to another variable, which the main could?
Oh, yes, you can, because their location is bound to the lifetime of the program, not to the function. So ff here will not go away once function 2 ends. So I could pass an address of ff, and that's valid.
Oh, because you could pass that address to the main function.
No, you could pass you could do that to the main function. Yeah. So you could pass an address of ff and return that and receive that in the main function. Yes. So
okay.
with no more normal variables like f here, I can't pass an address of f because as soon as this function ends, f will go away, so the address is no longer going to be valid, right? I'm going to be
Okay,
reading
just
old memory.
pointer inside this function and then assign that value into for ff, and then you can
Yes, I wouldn't think of it like you have a pointer to ff. But yes, you can think of it that way. Like you can think of it like this. It's rather more like you have the location of FF, and C allows you to just like write to it, right?
Yeah.
Yeah, that's correct.
Okay, thanks
Okay,
a lot.
no worries. I'll just leave you to hand. Okay, so function 2 here is this magical function, and this can access F, FF, E, A, and B, right? But it can't access C and D, and that's perfectly obvious because it's like, as I said before, it's hidden inside function 1. If it isn't, that's okay. This is something that a lot of people who are just starting off don't understand. So what will happen is that they'll have like a function like, I'm just going to call it A, right? And they'll have a variable inside this for I. Maybe they're using it for like a loop or something. And then they have another function for B, and they go, oh, I can't use I again, so I'm going to call I1 or I2 or J. And then they go K. And then they, at this point, they've realized they've made a mistake, right? And they go, okay, now I'm going to do L and then M, and then they've gone through the entire alphabet and they keep going, right? You can use the same variable here, right? Because the variables, like basically the variable that you're addressing is bound to this, and so it means it only exists within these limits and it's only accessible within these braces, and that includes if statements as well. So if you have an if statement here that's like some condition, right? And you create a variable here. I guess I can just use J, right? I can also create a variable in here. These are different variables. They're bound to the braces. They also go away at the end of the braces. And static functions are the only static variables are the only difference there. And I always. However, function 2 here cannot access G. The reason why is because G is declared after it, so it can only see stuff before it. It could still technically access it if you marked G above it as extern. Extern is something you don't have to worry about. I'm not going to really go into it, but there's a way to do it. It's technically still accessible in quotation marks. But it is currently not visible, right? Function 1 is the exact same idea. It can access A and B, C and D, and can't access anything below it, and obviously can't access anything inside of functions. Yeah, function 1 cannot use E and cannot use G. Unless you create an external variable above, yeah. As with anything in C, you can always break the rules. Now, variables deallocation is a bit interesting too. We are probably going to run overtime because I did all those extra answers to questions. But we'll see that most of the questions I talked about will make the future explanations easier, so it'll be fine. Functions 1, variables that are deallocated at the end of function 1 will be C and D only, like it won't deallocate any of these. These are bound to the lifetime of the program, meaning they'll exist forever until the program ends, then they'll go away. At the end of function 2, only F will go away. FF will not go away because obviously it's the lifetime of the program. So the thing about that you have to remember about deallocation is that deallocation and allocation, when we're talking about variables like this, are mostly just a user thing. They're not actually a computer. The computer doesn't actually like deallocate them. It just basically forgets about them. And that's kind of the same concept with free. So malloc free is basically when you go, okay, I don't know when I'm gonna. There's a few reasons, right, that use malloc free for, but the basic idea is I want to create some memory somewhere, right? I need to access some memory so I can put something in it. Maybe like store a game engine or store a user or store I don't know, an avatar. I don't know, like some kind of you're building a game about them or you're storing a bunch of movies or TV shows or whatever, right? Um, but the problem is that I don't know when I'm going to deallocate it. I don't know when I'm going to stop caring about this variable, right? And the reason why is if I'm building a user application, the user may want to keep it on forever, right? They may just want to like have a bunch of their movies downloaded forever and ever and ever, right? Another reason would be like I'm using a linked list, and so it's very hard for me to determine when that linked list element's going to go away, and I can't really tell the program that in a nice way. And so when you have situations like that, we basically have what we call manually controlled or manual memory allocation or manual lifetime management, right? Where we're manually telling it where the lifetimes begin and end. And so the other reasons that you do it too, like for example, if you want to return something from a function, like return a pointer to something from a function, right? But that's effectively the same thing as I said before, right? When you're returning a pointer to something, you're asking for the lifetime to be extended, right? And in cases like that, you don't know when it's going to stop being extended, right? Because that function could hold it for the rest of the program. And so for that reason, you need to manually control the lifetime. And programs like Python and stuff, they don't have that because they have what we call automatic memory management, where basically they do something called a garbage collector, which you can think about it as like a real garbage collector, right? When you're done with your memory, you chuck it in your bin and you forget about it, and then you hopefully the garbage collector comes, right, and comes and picks up your bin and throws away everything that you're no longer using, right? That's roughly what it is. The only difference with most garbage collecting languages is that they stop the entire language from running. So it's almost like if every time, every Thursday or Tuesday, whenever the garbage man comes, the whole world just stops. He comes, he picks up the garbage, he puts in the bin, and then once he's done, the whole world starts again. And obviously those stops and starts can be problematic for certain programs, so sometimes we avoid it. Yep, I talked about F and G already. G is going to last forever. F is only going to last within this function. FF is going to last also forever. When I say forever, I mean till the program ends. And we can see the answers here, right? Lifetime or program. Okay, let's go into storage and compiler commands and stuff like that. So hopefully that answers your question, Tay, about malloc. But effectively, it's just saying, hey, I want some memory. And so what malloc does is it gives you a certain amount of memory. So you can say, I want like 4 bytes of memory or 10 bytes of memory. And then once it gives you that memory, it gives you a pointer to the very first location in that memory so that you can write to it. Okay, so we have some storage here, which is just a located pool of 2 integers. So what we're going to do is we're going to chuck this into a compiler explorer. I don't really want to resolve the answers, so I'm just going to do it here. I'm going to turn off my camera because just make it smoother. And you can't really see me anyway. And you can see me playing around stuff. Okay, so what we're going to do, I'll turn it back on afterwards. Oh, I'm sorry. If you really care. I guess it does make it more personal. Oh, okay. I'm going to turn it back on in a second. Anyway, let's grab MIPS. So we're just going to grab MIPS and kind of briefly give you an idea, and not 64-bit MIPS, because that's a hell that I never wish upon anyone. We're just going to grab 32-bit MIPS, and we're going to look at a few things here. And I'm just going to kind of give you a rough introduction to what assembly is and kind of a way for you to start to kind of realize and recognize the code. So the first thing is that this tool is a freaking lifesaver, but isn't really that useful in this course. And the main reason why is that we use such a different variation of MIPS that most of this is going to be irrelevant, right? So for example, you'll never see add IU, you'll just use add, right? Add IU basically means add an immediate to an unsigned integer, right? That's what it means. So this is your immediate number, it's like a constant. And then an unsigned number is basically just don't overflow, or rather allow overflow and don't like do the whole negative thing. It's kind of confusing, but basically unsigned integers typically mean just allow overflow, whereas if it's non-unsigned, it won't allow overflow. Because that's the thing that you guys probably learned about 2's complement, is that when you're doing addition with 2's complement, you don't have to care about the fact it's negative or positive. So basically, the computer only really cares about unsigned versus signed for something called overflow, which is where your number gets too large and it wraps back around to the beginning. But anyway, so you don't really have to care about any of this. It's a lot simpler, but I think it's still interesting to kind of see how it maps. So the first thing that we realize here is that we have a variable S1, right? And we see that our S1 variable is located somewhere here, right? And so what this is a label. And so this doesn't actually exist. This is basically just saying, hey, this is kind of like a pointer on address, right? That's what a label is, right? So this is relevant to address that masks where this data is being stored. So we interestingly have 2 variables stored, right? And this is what we call a global or a data segment. If I turn off the directives and hurt everyone's eyes for a few minutes, and then find S1. S1's here. We'll notice that there's a data segment here. And what data basically means is it's effectively just like global is a rough idea of what it is. It's basically just data that's embedded into the program code rather than into the program stack or the heap, and the heap is where malloc occurs. So it's kind of like embedded into the code. So it's kind of like if I don't know if there's another way I can explain it, but it's like it's stored within the file itself, if that makes sense, right? So when it's loaded into RAM, it's loaded along with the instructions. Did the internet just do a flop? Let's see. Yeah, it says I am fine. I've got 500 up, 0.808 seconds delay. Is that where you treat strings and binaries? Kind of. Strings and binary are typically stored in read-only data segments or in global segments, but yes, they're stored within the file itself. That's not too relevant. For you guys, you'll just store them in your data segment because we're lazy when we're writing MIPS in this course. But yeah, so we'll see that we have this ASCII here, right? And this is going to be stored in data or whatever. Yes, it's a language. But importantly, it's a very low-level language that you run immediately on the machine. So basically, the machine can run MIPS. It has a called disassembler that will convert this MIPS into raw machine code, which is like zeros and ones effectively. And every instruction has an interpretation. So for example, this instruction here may be, I don't know, this in machine code, right? That's a weird way to do machine code. I don't know, it's like this and no ones. I cannot apparently type it, but that may be it. It's going to be 32 bits long because every instruction in MIPS is 32 bits. You can presume there's a bunch of zeros at the front, and that may be the actual interpretation of this instruction, right? So it's just like a language, just like C and Python, but it's much lower level. And so what we notice here is we notice a really cool thing, and we notice that we're loading a constant value into 2, and then we're adding to that constant value 20. We're adding to that constant value 25956. Also adding 4, but this is because it's being highly optimal. If we actually turn off the optimizations here, we'll see a much nicer change. And the big change is that we'll see there's an OR. It's just trying to be too clever for its own good, because it hurts my example when I'm showing it off and optimizes things. The rough idea here is it's loading a constant value into a variable, and this is kind of can be thought as a variable, and then it's doing an OR, a bitwise OR. So basically, if both bits are 1, or if one of the bits are 1, it will set it, right? And so I can kind of show you what this means. So if I load my value here, and we'll change this to a nicer, this is a tool I made, this will be relevant next week. And I load another value here, and I ask it to force the int size, it'll be 32 bits, that'll be fine, go. Okay, so what I see here is that when it does this 2 ORs, I get my 32-bit constant here, right? And so what's happened is basically it's loaded the top bit, and then it's loaded the bottom bit, right? As you can see, this was the top bit, and this is the bottom bit. And it's flying them together to produce the same constant. I notice these are my hex codes. Now let's do a bit of ASCII on this and figure out what these hex codes actually represent as characters, because maybe that's for the reason why. Because I don't see string DEF anywhere. I see ABC, but I don't see DEF, right? So let's just try to find it. So if we look at hexadecimal and we try to find D, right, we'll notice that D is 4, E is 65, and 66 is F. And so what we've noticed here is got F, E, D. So it's basically created a integer that represents the string rather than having to load each character one by one, right? So it's been really clever. And compilers do this all the time. That's kind of like a really cool thing about this. And the most important thing about this is the way it's stored. So this is stored as a string, right? Because this is a pointer. This is an array. So this pointer is saying it's pointing to some address in memory. It's pointing to ABC. So this is located somewhere in memory, LC0, right? And this is located directly on the stack, directly inside S2, directly inside that variable. And so effectively, what this means is that we get some really cool effects as we start to make it larger. You see, we make it larger and we get DEF as a string now, but it's doing a bunch of weird things with it's basically having to load and write it. This means it's storing the string inside the variable. That's effectively what this stuff is kind of doing, right? It's still very weird, but let's just keep making it longer and longer and longer and see what happens. Eventually, at some point, it goes crazy. It's freaking out. It wants to do as much as it can, right? Because it hates doing anything else. But if we make it eventually too big, we'll see what will happen is it becomes a mem copy. It's given up, right? It's tried to do all these clever tricks if it wants, but at some point, it's just going to do a mem copy of this string into memory, right? Which is probably what you would do, right? Ways, go ahead.
Uh, we are looking at the concept of like MIPS language, but is
Yeah.
this basically a version of assembly that we are doing?
It is literally assembly, yes. Assembly is a
So
dialect language, so every assembly language can be different for every processor.
yeah, so I was just wondering if you could explain what actually assembly does or what it actually means, because I don't think we have been explained that properly.
Assembly does basically just refers to a, a series of I guess a rough definition is assembly is a mnemonic, which basically means like a way to kind of bind some words that hold some other meaning. So for example, the word adiu holds some kind of raw binary meaning. So it could be like, as I said before, like 0101 something, right? And so basically it's just a mapping between machine code and human readable code. So in the olden days, Grace Hopper, I don't know if she actually wrote, I know she did a bunch of queer stuff. I don't know if she actually wrote one of the things. She did write one of the first languages ever. Um, like very first programmers would have written in raw binary. So they would have been writing like this, right? Obviously, that's very tiresome. If your entire code base just looks like this, raw binary is gonna like drive you insane. So some developers thought, well, why don't we give patterns to this binary and start giving them human readable names? Like we say, this pattern here is add 2 2. This pattern here is subtract 2 2 1. Right? Or maybe this is like something like this, right? And this is like the constant 100 that, right? And so on. And so they basically gave meaning to a sequence of binary digits, and this is called assembly, right? But there's so many different dialects. Yeah.
That makes sense.
And then people were like, assembly's too hard, so they wrote C, right? And so C is basically what assembly is to machine code. C is like that to assembly, right? So I said importantly that every bit of assembly maps to raw machine code. Every bit of C is it's not very easy, but it's easier to see how the C maps to machine code than it is for other languages. Like if you gave me a bit of Python and said, what machine code does this produce? I would have no clue. But if you gave me a bit of C, I could see it, right? And other languages are similar. Like C sharp, I can pretty much recognize what machine code will produce, even though it does use JIT. And it just comes with experience, right? And you'll see for this course that you get better and better at it, right? And so cases like this, I can look at this code and you will be able to too, right? And go, obviously, I know where this is going to be stored because it's a stack variable. It's going to be stored in stack, right? And it is, right? And I can kind of recognize what code will be used to produce it. And that's how you write assembly, basically. You write the C version that you convert across to assembly. Not always, but for this course. Okay, there's quite a bit more, so we're just going to race through the rest of it. That's unimportant, then cover the most important part, and then we'll go into the lab. The lab is much shorter. Most people completed it. Most people didn't complete it on time 100%, but most people found, actually, it was kind of long this week. Okay, so I'll keep this to about 15 minutes. Compiler commands, this is kind of irrelevant for the course. I don't really even know why this is here, but to kind of roughly go over it, this produces the machine code, as most of you know, right? You run the code from this. This unwraps every single macro. So every macro in your program gets unwrapped and placed into its value. So for example, this becomes 10, and we can see that right here. If I replace this with -e, we'll see that I created this is C code, right? So even though I'm compiling it, it's producing C code. And what it's doing is it's converting all the macros. So it's done the hash include, and we can see the hash include here. Like for example, I could show you what a file looks like on this system. A file is where, here's a file. So this is what a file looks like. I'll go for that in a second. File has flags, has some read pointers, has a lock somewhere. Here's my lock, has my offset, right? So this is a file that you can read from. This is what the interpretation is. And then this thing here is probably a buffer, most likely. It does say unused. I don't really know why, but sure. There's a bunch of calculations here that seem really weird, but maybe it's a buffer that's used for something. No really clue why they care. Macros are effectively text replacement. So when I do something like this, like hash define 10 to n, what I'm saying is replace every n in the program with 10. So it's just text replacing this n here with a 10. And hash include is basically just saying replace this line with every line of the file called stdio.h. So it's going to grab the file, the library file stdio.h, which is this file right here, and copy and paste it into here. I believe it also removes comments. The other ones are kind of relevant. S produces assembly. So this will produce your assembly file. Basically, it produces this, right? And then dash C produces an unlinked machine relocatable code. No hash defined variables are typically uppercase, like n, but the word itself would be lowercase. But yeah, so typically all the things are uppercase, all the names. That's just so we can recognize. Now this code here, this is kind of important, just as a recap. So when you don't have braces, what will happen is they will add braces for the next statement. I'll go for that in a second. So the next statement, so for example here, the braces around 0 will also be added around here, right? Because it's just the next statement. So basically automatically adds it. Whereas for this third one here, it will only add it around 0. It won't add it after, right? So what will happen is that 1 and 2 are going to be identical, but 3 and 4 are not, right? So for 3, it will just add it for these two expressions. It won't add it for after. And so for that very reason, I highly, highly, highly recommend only write it on a single line if on a single line, right? So if you don't add braces, only if it's on a single line, right? So like this. If you put it over in 2 lines, what will happen is at one point you won't be thinking and you'll probably add an extra line and it will cause problems, right? And it won't tell you any warnings or anything. Though I do think it may give you a warning if the indentations like this, it may. Depends, I guess, on your settings. GCC and DCC. GCC uses something called Clang, which is effectively GCC. There's 2 main C compilers out there. If I look at here, this is GCC, for example. There's also Clang, as you can see here. They basically are the exact same thing. There's also ICC, but you can ignore that. Yeah, it'll work. It just will grab the next statement. We'll just do this. So it won't grab the after. But DCC is effectively an addition. So what it does, it adds better compiler errors. It adds runtime security. So basically when you access variables that you shouldn't, it will warn you. It will give you errors and crash. It does a bunch of other things. But basically it's just like a safer version of GCC. We can use DCC for almost everything. There's a few things that we can't use it for. I believe we can't use it for signals. You can't use it for, you learn what signals are later. We can't use it for something else. Thank you. I do cover a lot of stuff, so I do expect people to not remember a lot of this, but you'll see more and more later on, right? And the idea is to expose you to a lot of this stuff. Memory address recap. This question is kind of boring, but effectively what it is that you have some kind of, as I said before, the thing about pointers is that they have a value and an address because they are themselves an object. And so P here is located at an address somewhere. For example, it could be located at address like 100 or 200 or whatever. And so what we're doing here is we're binding it and we're saying P now points, or the value of P is equal to the address of N, right? And N0 here is just going to be the address of 42. And for arrays themselves don't exist. So the address of an array is always the address of its first member, right? So the address of n here is going to be identical to the address of n0. So that's just a preference thing they've done here. And saying that you shouldn't grab the address of n, instead you should just say n, because the address of n could actually also be different if you pass in a function, stuff like that, because it can have weird things, because if you pass in as a function, an array decays to a pointer, which I'll mention in a second, so don't worry about that. But anyway, so here it appears, and here's the size of an int, which is 4. So when we do something like this increment here, we increment n, what's going to happen is it's basically going to increment 42 here to 43. Like, that makes sense. But because p points to n, when we ask for the value inside the address of p, so we're not asking for the value of p, the value of p would just be p. We're asking for you to dereference P and follow where the value of P is. And once you have followed that value, tell me what the value of that is. So effectively, it's going to follow P to N and then find out what the value of N0 is, right? And so the value here would be 43 because we updated it 43. If we increment P, what will happen is it's going to move to the next value, right? So when you increment a pointer, this is where the type actually matters. And so this is kind of a weird part as well, is that pointers types don't matter whatsoever to the actual assembly, right? Assembly doesn't have types for its pointers. It doesn't have types whatsoever, to be fair, but I guess it kind of does because it's got like I, right? IU, which is like unsigned. It's got like floating point addition and stuff, right? So it has kind of types in quotation marks, but the actual memory itself, the actual data doesn't. And so the same thing kind of happens here. This could be a void pointer, which is basically a pointer of our type. This could be a float pointer, it could be anything, and it'll be stored in the exact same way, right? The only difference matters when you increment it and when you dereference it. So when you dereference it, the number of bytes that it takes and the type of those bytes that it takes matters in the type, obviously. And when you increment it, the number of bytes it moves along is equal to the size of the type. So basically, when we say P++, we're going to move from 42 to 23 because it's going to increment it by 4 because the size is int and the size of int is 4. So it's going to move from this to OX7FFF00000004, right? Because it's going to increment the address by 4. And so when we print it out, we'll get that value I just said before. When we find the address of that value, we'll find 23. You can see like here, I go through each of the comments, right? So after the shoots, have a read through this. If you're still not understanding everything, obviously send me an email as well. It's also fine. And this should kind of explain around a bunch of the kind of smaller parts I maybe slightly mentioned, but may not go into much depth. So for example, one of the things here is the address of n. I said is the exact same thing as n. And you may go, well, why is it the exact same thing as n? And you can see the arithmetic here, right? And this is kind of what happens. When you do n like this, what happens is it adds 0 to n, right? Because n is still like a pointer, right? It's an array. So it's a pointer to the first value 42. Or quotation marks can be thought of. And so when you add 0 to it, you're asking to add, move nowhere basically, stay where you are. And so when you add 0, then you dereference it, right? And then you take the address of that. Obviously, the dereference and the address are going to cancel each other out because one follows the pointer and the other comes back. And so basically it just becomes n plus 0, which just becomes n, right? And for the same reason, you can also reverse it, right? And you may have seen this. This is kind of a party trick that people like to show. For the same reason that we can actually show that p is also equal to this, right? Because if we take this way, we get 0 plus n, which is the exact same thing as 0 plus n, which equals n. And so for that reason, we can say that n of 0 is equal to 0 of n. And this works for any constant. So you can say n of c equals c of n, or any constant. 0 is less than equal to c, which is less than the length of n, right? The length of the array. And so this is kind of like a nice way, right? And obviously I would never recommend to write code like this, but you can, right? Okay, so we can skip past that. That's not too important. And we got pointer arithmetic, and that's it, right? So GDB, there's a recommended resource here. Have a read through it. It's really kind of quite good. It's a bit of an information dump, as in there's so much information here. If you want like the Cliff Notes version of it, I read this up probably a year ago, maybe 2 years ago. It's very, very simple. Oh, I clicked the wrong one, didn't I? I meant to click this one. It's very, very simple, and it kind of doesn't go into much depth. But basically, it kind of just tells you the rough idea of how it works. There's 2 ways to run it, how to use command line arguments, how to go to the next line, how to skip a line, how to set a breakpoint, right? And so some of these words you may not understand, but like you could still just play around with it and see what it is, watch variables, for example, and stuff like that. GDB, it's just I don't know what the G stands for. It's a debugger. I think it probably stands for like GNU debugger, probably. But basically, debugger lets you go step by step through your code, like line by line, and see every line of your code and what happens after it. And the Valgrind is just a way to see what happens if you've got any memory leaks, i.e. you've got to freeze something that you mallocked. There's other stuff here that may be somewhat relevant to like home computing. If you want to set up VLab, there's interesting things for VLab and SSH and stuff here. And technically Java as well for 25011. And there's a Go tool here, which is not relevant unless you're doing 252.1, but can kind of show you how Big O works. right? You can kind of see some pretty graphics. Anyway, so other than that, we're just going to do point arithmetic and stop. There's not too much more after this, but there's literally nothing else. So let's create a new file. This is kind of important, so we can cover it. As I said before, I basically spent the entire time on pointers because I think that's the hardest part of 1511. I think the rest of it, most people can kind of grab without too much struggle, but recursion is something I will probably do a video on. Okay, so we have X here. It's located address 1000 with value 0, and P is located address 2000 with value 0, right? Again, the pointer here, the pointer is located at address 2000, right? And it points to null. That's basically what this means, right? 0 can be thought of as equal to null. Technically, that's not entirely true. There's certain systems that can null as something else other than 0, but for the sake of programming, you can think of it as 0, and furthermore, C states that if you do anything that makes it basically regarded as 0, it will convert it to null. So for example, when I did this up here, well, this is basically doing, I think there was a question about this, I ignored it maybe by accident. I just remember it now. And the question was, I think, asking what does this do, right? And so the rough idea of it is that this is a value, it's a pointer. And so when we do this not, we're basically saying, hey, if this is equal to 0, the not will make it equal to 1, right? That's what not does. So if it's equal to 0, then it will equal 1, and therefore this if case will pass and it will allocate it. So if it's equal to null, this if statement will pass and it will allocate it. If it's not equal to 1, right? Sorry, if it's not equal to 0 and it's equal to like 10 or something, then the not will turn it to 0, right? Because how not works is not 0 is equal to 1, not anything else is equal to 0. And so basically, if it's not 0, it will convert it to false and then not run the if statement. It's a very nice way. I write stuff like this a lot. The most common thing that you'll ever see is a string length function. This is technically not the most fastest way to do string length, but it's roughly as fast as you can get it. And the rough idea is something like this. Right? And you know what? Let's do it this way. Right? And so this is probably one of the most common versions of string length that you see. You may also see it as like an integer that increments every single time, like us like this, then returns I. They're effectively the same thing. And the rough way of how this works, right, is that it creates a pointer P that points to C, your string. And this is, if this is equal to 0, right, it's going to equal to the /0, right? And the /0 is equal to 0, so this will be false. Else, if it's not /0, it will be true. And so basically this will only stop at /0, right? And so then you're just incrementing all the way through. There's no need to have anything at the end of the for loop. I could just do empty braces or a single semicolon. And then the very end, you just find the difference between the lines, which will tell you the length of the string. The fastest way, if you care about it, is using basically you'd go 4 characters at a time. And you just check whether or not any of the bytes of that character is wrong, or you could go 8 characters at a time and check whether or not any of the bytes of that 8 characters are wrong, 0, right? And if any of that bytes that is 8 characters is 0, then it's more efficient. Yeah, don't worry about that. Yeah, so effectively, you don't have to care too much about it, but the rough idea of it is just that since P is an integer, and since everything is an integer, you can do these tricks around how C manages if conditions like true and false. Since everything that is 0 is false, everything that's not 0 is true. So you can do various tricks like this, kind of get it to work, right? And you see a lot in C code. It's because people in C code like to think they're smart, so they write very confusing code. That's not even that false. Okay, so for example here, our new value of P is going to be 1,000, and X is still going to be 1,000, and they're both going to be located at the exact same address, right? So P is still going to be at 2,000, and X is still going to be 1,000, right? And also do $P, or not asterisk P, which is going to be equal to 0, right? Because X is equal to 0. Okay. I'll put these on a new line actually. Make it look nicer. Okay. Now we set x to 5, and hopefully like that one's obvious, right? We set x to 5, x will be 5. Now asterisk p will also be equal to 5, right? Because you're going to the address of where p is located. Because that's very different. Yeah. The reason why this is wrong, I'll still explain it just because other people may be also confused. Is that when you go asterisk p, you're asking it to follow the value of p and to find where the value of p is located at. And so if I follow the value of p, I'm going to follow null. And so what's going to happen is this is going to dereference null and try to set the value at where null is located at to the address of x. For the first question, why is x 1,000 not 0? You mean yes, that is correct. That wasn't a mistake. Yeah. If it's summons, I do make, and that should also be 5. I guess I'd probably guess maybe it's a bit cleaner. We'll put this on the same line. Okay, there you go. And we don't have to repeat that so much. That was just my brain automatically doing it and not thinking. Okay, so the next thing here is $p equals 3. I keep saying $, for some reason that looks like a $sign to my head. Asterisk p equals 3, which basically means most of it stay the same, right? The only difference is obviously this is going to become 3, right? The statement's match up, but so will x, right? Because x is located at where the address of p is pointing to, right? As we've shown up here. So when we modify p by dereference, we're modifying the location of the value of p, right? And this is kind of where it gets confusing because there's a lot of words, right? So if I write the math sums, that makes sense. So you're modifying the location at the value of p. The value of p is the location of x. Therefore, modifying the location at you're modifying the value at the location at the value of p. So therefore, you're modifying the value at the location of the value of p, and the value of p is the location of phi, the value of the location at the location of x. You can see it's confusing for me to write out, but you're modifying the value at the location of the value of p, which in the value of p is the location of x. Therefore, you modify value at the location of x. I don't know if that made more sense. That just kind of got me more confused. But hopefully, like, eventually it will click. I find typically the point is the less you think about them, the easier it is just kind of like conceptualize that there's 3 states for them. There's the address of the pointer, right, 2000. There's the value of the pointer, which is where it points to. And then there's the reference of the pointer. Diagrams can also make sense, right? So here you could put in a diagram to x. I won't do it, we don't have enough time. But yeah, so you could point like the diagram of x to a p to x and say when you're modifying x, you're following the diagram pointer. They're hard. Okay, so the next thing here is we're grabbing x and setting x to the address of p, right? Well, I shouldn't say the address of p, the value of p, right? And so when we're setting x to the value of p, we're setting it to basically the address of itself, right? Because as we know, the value of p is equal to x, right? And this is where you're kind of getting confusing because you're saying the kind of the same words over and over again, right? But we can just kind of replace p here with its value, right? If this makes sense. So we're just going to grab this value here and replace it. And maybe this starts to make more sense what we're doing, right? Is we're basically just going, okay, set x to the address of itself. In this case, if we do that, x becomes 1,000. And so does with this, this is what we call a cast. So a cast is basically when you want to change types. So P is typically what we call it's going to be a uint pointer type. Basically means it's an unsigned pointer. That's an integer, I guess. Some people would say it's size T. Those people are wrong in quotation marks. It's often size T. You'll see in the course, we'll call it size T. Size T refers to the size of variables. So when you go size of int, the type of this is size T. And so people often think, well, therefore, if we're allocating things of this size, pointer must also be this size, and that's technically not correct. It often is for cases that you'll be using, but this is an important distinction. For the sake of the course, just use size t, it will be fine. So what they're doing here is we're grabbing this value, right, and we're saying cast it to an integer, right? So it used to be unsigned, now it's going to be signed. Now this is obviously going to be problematic because integers are 4 bytes and pointers are 8 bytes, right? Even the size t is going to be 8 bytes, right? So if this pointer is too large, this will cause overflow, right? Or they will cause overflow or truncation. In this case, it could cause both because you're going from unsigned to signed. That can cause overflow and you're truncating it, so you could cause truncation, which is going to be problematic, right? In this case, it's fine because the numbers are small enough. If these were large, it could be problematic, which is why I don't like this part of the question. Because pointers are always unsigned. So do pointers have a cutoff? Pointers don't have a cutoff, but on modern systems, they are effectively have a cutoff because the way you can find out how much memory you can have on your computer, for example, is just to do this. You go 2 to the power of, for example, a 32-bit computer, it'd be this. That's like the maximum memory that you can have on the computer. So if you grab this value and then you just divide it by a bunch, you just divide it by the same thing over and over again, like 1024, I think it's 3 times. That's how much memory or RAM can exist on a 32-bit computer. It's about 4 gigabytes. On a 64-bit computer, it's significantly larger. Like that's a lot of gigabytes. So most modern computers don't have that much memory. So most modern computers typically only use like 33 or 34 bits. So technically, they're typically quite fine to do this cast because most of them will fit within the 4 bytes. But especially even on if your computer is more than 4 gigabytes of RAM, this has a chance to fail. It's probably not going to cause overflow, but it does have a chance to fail. Actually, it could definitely still cause overflow. But yeah, they cut off. Theoretically, practically, they probably do. So that's what's going to happen here. This value is going to become 1,000 because the address of x is 1,000. Therefore, the dereference of p is also 1,000. Then finally, we're setting x to the address of p, which is going to be 2,000. Right. So basically, this becomes 2,000. So is this. Right. And then we're setting p to null. This becomes null, which we can just say 0 in quotation marks for this course. Just say it's 0. This I'm just going to do like this. Like, what does this even mean? You can't dereference null. And then the addresses of everything else stays the same. And then when they finally try address null, this is going to cause a crash, right? Because what memory is this at null? The reason why it causes a crash is kind of interesting. Technically, C doesn't say it has to cause a crash. C says it's undefined behavior, which means it can do anything. So technically, what could happen is it could just work, right? That could be your undefined behavior, right? But on most modern systems, null or 0 is kernel memory. And kernel memory is stuff that belongs directly to your operating system, like your computer, like Mac or Windows. And obviously touching that stuff is very bad because if you could touch that stuff, you could like change what users logged in, you could change like what permissions you have, you could do everything in the world, right? And so operating systems implement something called like security rings that basically say what programs have access to what, right? And so, for example, your user programs don't have access to kernel memory, so they can't modify 0, right? Because 0 is kernel memory. And so that's the reason why it crashes. And that's the reason why you get seg fault, because you're accessing, it's a segmentation fault, a segmentation of the memory. Sometimes you can get page faults as well. Which is kind of interesting because what that means is that drivers, a driver is something that effectively is a special program that interacts with like outside things. So for example, your mouse requires a driver. It basically like interacts with lower level components of your computer. So like your screen would have a driver and so on. And so if your computer ever blue screens or crashes, like 99% of the time, it's going to be due to a driver. And the reason why is that drivers have access to kernel and have access to a bunch of other things. Which is one of the reasons why inserting like a USB drive into your computer is problematic because it could be a driver that installs in your computer then has access to like kernel memory and stuff like that. Typically, that's harder to make it install, but it can. So drivers are nasty, but that's also why they crash, because they have more access to everything. So if they change something, it could be much worse. Is that why overflow exploits work? Overflow exploits work similar to this, yeah. So when programmers write code like this is why overflow exploits work. Typically, overflow exploits could be buffer overflow as well. So overflow exploits is a type of a security problem that relates to basically what happens when you make numbers too large. So when you make a number too large, it can't represent it. So for example, if we have an 8-bit number, right, this can represent everything between 0 and 255. And so when we try to go bigger than 255, it can't represent 256. So what's going to happen is it's just going to go straight to 0. Now, if this is a signed number, as you probably learned in the lectures, this will represent any number between negative 128 and 127, right? The reason why it's one larger on this size rather than this size is because 0 is perceived to be a positive number rather than a negative number. So technically, this has the numbers between 0 to 127, and this has between negative 128 and 1, negative 1. So what this means is that that these ranges are the same length, right? So this range is going to be 128 characters, and so is this, right? But that's the reason why it's big on one side. Okay, so if we have a number like this and we try to go too large here, what will happen? So for example, if we try to represent 128, it becomes negative 128, right? So it wraps around to the smallest number. And underflow happens too. If we try to go negative 129, it will wrap around the other way. So that's overflow of numbers, but there's also something called buffer overflow, which is probably more what he was talking about, which is the concept of when you go past the end of an array, what happens. So if my array like this is 4 bytes long, right, and I try to write to number 5, what's going to happen is it's going to write to like memory over here, and this is very wrong. And so what will happen is the program will probably allow it unless it's like memory that's outside of your program space or address space, which is like address space is just things accessible to your program at that time. And so if I write to this like 20, it may work, it probably will, even though there's no memory there, but there is memory there, right? That's the thing, right? So if we look at this in terms of like our big image, like as I said before, you can kind of think of it like one big array, right? And I have my A array here, which consists of 1, 2, 3, 4. There is memory right after the 4. The only problem is that we haven't told the computer any intention of using this memory, which means that it could be anything. So for example, if we do this and then follow up with an integer like I, it could place I right here, right? So it could place I right after the 4. And so when we access at number 5, we don't know what memory is there. And it just writes to 5. So what will happen here is that this will probably edit I. Not necessarily, but it's a bit more complicated than just saying it always will access I, but it can be thought of as accessing I. And that's the way buffer overflows work, is that you give a program enough data that it can't store it within its buffer, and then now suddenly it's writing data outside that buffer, allowing you to modify the local variables of that function, giving you access to things, such as maybe being able to write a flag that checks whether or not your password is true or false and being able to set it to 1, meaning true. Or, for example, it can become even more extreme where basically you can change, like if it's got a function pointer or something, you could change the function pointer, meaning it could jump to your own code that you have inside the system. So you could basically hijack the function and run whatever you want. Like it can be crazy. Which is one of the reasons why we typically make the stack non-executable, which would prevent people from being able to execute arbitrary code. Anyway, we've gone way overdue. This was the longest, my longest chits. Hopefully, most of you didn't mind it going over.